Start with the exercise number 3. So I call EX3 problem 1. And this is a very simple task to deal with to make yourself familiar with the plane wave. So a plane wave shows an electric field of a certain intensity. So we have here that the electric field is assumed to be a real vector, and it's 2 volt per meter. So this is the value, and we have it's directed in y direction. So perhaps I write it like this. This is E naught times the unit vector in y direction. So in the lecture we assumed that the plane wave, its polarization is polarized in the x direction, and here I now assume that it's polarized in the y direction. And it's propagating in the positive z direction, so also this will propagate in the z direction, this plane wave. And the question is, first calculate the absolute value of the magnetic field and give its unit vector of its direction. So we know that the magnetic field, of course, must be perpendicular. So I will write it like this. This is H naught. So this describes the intensity of the magnetic field, and I call EH, I will call the unit vector which points in the direction of our magnetic field. And now the first question is, calculate the absolute value of the magnetic field. So this is a very simple question, because we know that in a plane wave the electric field and the magnetic field are related via the field impedance of free space. I can say that the H naught is always given as E naught divided by Z naught, where we have the field impedance in free space. Z naught is 377 ohm. So we will see that we have here 2 volt per meter divided by 377 volt over ampere. And you see here the volt will cancel. And if you calculate the value, then you will get a value of 5 to the power of -3. And of course we have a unit of ampere over meter. So this will be the magnetic field. And now the next point, it's now the question, and give the unit vector of its direction. So we know that the wave vector, I write the wave vector here, it's somehow k naught times IEZ. And so we see that the wave propagates in the z direction. It is written in the task. And now we must remember, of course, that perhaps first I sketch here the unit vectors. EZ, this is the right-handed coordinate system for the unit vectors, for the rectangular coordinate system. And we know that the wave propagates in the z direction, and also this means that also the pointing vector will point into the z direction. And now we know that the electric field points itself in the y direction, and we know that E cross H must give the direction of propagation, must get the direction of z. So you see here, if I now use my right hand, then you see the electric field points in the y direction and the pointing vector points in the z direction. So you see the magnetic field must point in the minus x direction. So we will have, from this we will see that EH, the unit vector, will be minus EX. This will be the answer to the question. Give the unit vector of its direction, though the unit vector of the magnetic field points in the minus x direction. So did this become clear, or are there some questions?
Sorry.
Yeah.
So if the problem doesn't mention it, we just assume it's in free space.
In most cases, I will assume that the plane wave is in free space. Or if I don't say something about a dielectric, then the plane wave is assumed to be in free space. Of course, up to a frequency of round about 10 gigahertz to maybe 15 gigahertz, we can assume that the air behaves almost like free space if it's not too forky and so on. Other questions? So then the next question is, we have to calculate the absolute value of the power density of the wave. So this means we calculate the time average pointing vector, and we know that the time average pointing vector is always given by 1/2 E naught. Here in our case we only have to take the absolute value squared divided by z naught, and if I use the vector notation I would have to write here Ez. But if I'm only interested in its absolute value, then we can say that the time average pointing vector, which describes in principle but the power density carried by our plane wave, can be calculated by 1/2 E naught absolute value square divided by z naught. So it's very easy to calculate this value. Of course, as the time average pointing vector will be then 1/2. We have here 4 volt square over meter square divided by 377 volt over ampere. And of course it's 2 here, and you see we have in principle the same value. It will be 5 times 10 to the power of minus 3, but we will have of course a different unit here. So here we will have as a unit watt over meter square. So you see, this is what I always tell you. If you do the examination, of course, it's very important. In the most cases, the solution of a task, if I want to have the overall value, then we have the value itself and the unit. And if you omit the unit, of course, this will result in a error in solving the task. Of course, the total value is composed always from a value and its unit, of course, and you see here, due to the values are used here, we have the magnetic field and the power density show the same value, but of course they have different units.